All right, this is a big moment in calculus for us. So, we're going to talk about derivatives. If there's anything you need to take from taking this class, it is derivatives, integrals, and then like one other thing which I've forgotten, which is great that I've forgotten it, because that tells how much I've retained. But it's fine because I actually myself haven't completely taken this class yet, so I'll find out later. So, derivatives are very important. Before we get to this definition here, this huge nonsense of variables, we're going to talk about what the derivative really says. It says it's the rate of change of a function. It's how something changes as it's how your function changes as you change x very slightly. How does the function change as x changes? That's exactly the question that a derivative answers for you. So if x is modified by a tiny, tiny, tiny amount, then how does the rate of change of that function, or how does the function itself change? Also by a tiny, tiny, tiny amount? By a lot? That's something the derivative measures for you. So what we're going to do is we're going to actually derive the definition of the derivative, because basically what this entire thing says is the derivative, this d of x over d of x, or this d of f over d of x is the signature for derivative of this function f of x is equal of any function f of x is equal to the function x plus h minus the function of x over h. We're going to talk about how we get to this thing, okay? So what we're going to do is derive the definition of the derivative. So we're going to use this function here, one of the simplest functions imaginable, to derive the derivative of, or to derive the derivative from. So let's think for a minute, how does this actual function work? It works something like this, where if we wanted to find the slope at any one point of this, because that's the derivative gets us, it gets us the slope at any given point, we can't without using a derivative, because we can't measure the slope on a curve, but the derivative gives us the slope on a curve. So we are going to derive it now. We're going to use this function, and this function is cool because you can represent what's going on here geometrically. So we can say here that we have this square. This square has dimensions x and x, which means that the entire thing here is f of x, x squared. So what we're going to do is we're going to change x very slightly. When I say very slightly, I mean really small. So we're going to take this x here and here, and we're going to add on a tiny d of x. D of x. So a tiny difference in x, hence the d. We're going to take a tiny difference in x. So this d of x I need you to think of as a very small number. Not a very small number that it doesn't exist, like a infinitely small. No, I mean a number that exists. It is a number that exists. It's just very small. So what we're going to do now is compare the change in area. So because the area here tells us how the function changes. The side lengths here tell us how the x changes. So that means we're going to have this x plus dx and this x plus dx over here. And we're going to see how we compare the area. So our total area, or our total change in area, df, so the difference in the function, is going to be equal to the total area minus our original starting area, because we want just the difference in the function. So we're going to say that the difference in the function is equal to the total area, x squared, plus, notice how we have oh my god. Notice how we have two long bits and then one square bit. So we're going to have two long bits, so 2, and the dimensions of this long bit are dx and x. So we're going to have 2x times dx plus another dx times dx. So we're going to have a dx squared. And then we're going to subtract this by the original area, because we want just the difference in the area. minus x squared. So now we're going to do a lot of canceling here. We're going to do a lot of little canceling steps. So our little canceling steps are going to involve this. X squared minus x squared is equal to 0. So we're going to have d of f is equal to just 2x times d of x plus d of x squared. Remember when I said d of x is equal to a very, very small number, but not an extremely, extremely small number that doesn't exist? Yeah, well, let's go back to our runners on how this works. So if we have runners that we represent with each, yeah, they have to run. So that's why they're sad. If we have runners that have to represent each term in this thing, as dx gets closer and closer to infinitely small, this dx squared approaches infinitely small way quicker than just this one d of x, because this one's squared, which means you're multiplying it by itself very tinily. So you can, as far as calculus is concerned, completely ignore it because the gap between this is so small. So, and if you don't understand the thing with the runners, I would encourage you to watch the previous video where I talked about how horizontal asymptotes change, and why we can use why we can only use the first term to solve for horizontal asymptotes. So as far as math is concerned, we can completely negate that part. Now, what we want to do is find the rate of change, which means we want to find the change in y over the change in x. Well, this here is our change in y, the change in the function. This here is our change in x. So we're just going to divide it by this. We're going to go d of x, or d of f over d of x is equal to 2x. This is very important. What this tells you is that at any point on the graph of x squared, the rate of change is this. So that means if we set this number here equal to 2, that means that the slope of a tangent line that runs along this line here with x squared, the slope is equal to 2 times 2, which is 4, which means the m of this line is equal to 4. So now what this tells us is the slope at any one point on this line. So this is the derivative of x squared, and this is it solved geometrically. So again, what we just did was we evaluated how the function as a whole changes as a tiny fraction of x is included. So that means that this derivative is that, and that we can then go on to find more. So now let's think about how this compares with our derivative definition here. So this df dx f of x just tells us that we're finding the derivative for this function is equal to fx plus h. Isn't fx plus h just this part right here? It's just the change in it's the total area now that we've changed it, minus f of x. So we want the change in the area. So we're going to subtract the original area over h. Where does h come from? So this h comes from this because when we are trying to find a slope, we do this. So we would go y1 minus y2. Well, just know that our original x is x. So we would go x minus, our beginning x, because we have to keep them equal. We have to keep the change side on the left if we're going to do this. And we're going to have x plus h over here, and then this is some y1 minus y2 if we're trying to do slopes. So x plus h is our first x that we use to describe it, and then we go minus x because we're trying to find the change in x as well, because remember, this whole thing has to be change in y over change in x. These two x's cancel out, we're left with just h. Now, just know that why is there an h here when we use dx's down there? Well, that's just because calculus uses the variable h to represent a tiny difference in x. So that's literally all it is to it. There's no specific thing. It's just that we use the variable h to represent d of x. So that's where the derivative comes from. Now let's actually put the derivative to use and solve using the derivative. So what we're going to do now is we are going to solve we're going to solve for the derivative and then use the derivative to solve for the slope and equation for a slope at any one point on a graph. So I'm going to keep this here. We're going to go question number 1. How are we doing on time? 10 minutes. That's not bad. Question number 1, we have this here, negative 3x squared. What is this? Plus x plus 3. I don't like how it's a negative in the front, I'm not going to lie. So we have this thing here, and we need to find the derivative of it. So we're going to plug it in to this definition here and use it the same exact way that we just did it. So we're going to go, we know the derivative of f over the derivative of f of x is equal to, and let's just say that this is our f of x. We know that it's going to be equal to this. So f of x. So we have to do, I'm going to keep it just down here at the bottom, so that way it's still visible. We have to go at the top, negative 3x plus h squared plus x plus h plus 3 minus negative 3x squared plus x plus 3 all over h. Holy crap. That's a lot there. So we just have to go simplify it. That's all we have to do is just go and do it. So I can ignore this for now because it's just going to be equal to that same thing. That's never going to change. So we'll just say now, we'll simplify all this down. So negative 3x squared plus 2xh plus h squared plus x plus h plus 3 minus, or that would be plus x squared minus x minus 3. Just do algebra right. Now, one little thing here is that when we get an h that is to any power greater than 1, remember just from how we derived our derivative that because this h is a really, really small number, hitting it with a power of 2 makes it a really, 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 really small number. So this, for calculus purpose, is negligible. So now we'll hit the whole thing with the 3. So negative 3x squared plus, no, not plus, negative 6xh plus, or no, minus 3x minus 3h plus, nope, negative 9 plus 3x squared minus x minus 3. Holy crap, that's a lot. So, how are we doing now? Let's just simplify all of this down. I don't know. I have a feeling I did something wrong somewhere down the road. Oh yeah, I did. Yes, I did. So this is supposed to stop off right there. Then that's supposed to be like that. Okay, that explains where I did something wrong. Because I was like, where's this 9 coming from? Because things should cancel out appropriately. And if you notice it really quickly, then you can get it correctly. Minus 6xh. Minus 6xh. Negative 3 times a negligible thing is 0. So plus x plus h plus 3 minus, no, plus 3x squared minus x minus 3 all over h. Let's simplify it one more time. So 3x squared, those cancel. Minus x, those cancel. Minus 3, those two 3's cancel. Now we're left with only terms that have h in them, which there's a reason why we're doing that. So negative 6xh plus h over h is equal to negative 6x plus 1. Okay, now that's how it should cancel out. So if you're left with any terms that still have h's in them, then you've done something wrong somewhere down the road with just basic algebra, almost like I had. So you're going to need to do it. So that means if you're left with some 3h over here or something like that, and then you divide and then you get like and then you divide, and then you get something that leaves an h in your answer, because that 3 actually wouldn't do much, then you've done something wrong. So this here is our derivative. So this is the derivative. So I'm going to box that. And now all this math can go bye-bye, but the derivative doesn't have to, because we have to do another step. Because not only does it want us to find the derivative, at least for this problem, it also wants us to find the derivative at x equals -2, which is something I actually forgot to write to begin with. So it wants us to find the derivative and then also find the equation at -2 for what the equation of a tangent line touching the graph would be, because you know that this graph moves something along the lines of that. And it wants us to find it at -2, which let's just say -2 is like right here. It wants us to find a tangent line that goes like this to the graph. And all of these questions will want us to do that, which means we're going to spend a lot of time on these questions. So now let's go even further. Yeah, we're good. I'm just saying to myself, do I want to do all the questions if I don't need to? I don't think I need to, so I'm just going to do one example, and then you'll know that how things cancel. You can just use the same rules that you used for limits to try to cancel and then multiply things out and then make sure things disappear. So x is equal to -2, so we will do 6. Okay, let's do this now. So first we need to find what it is at y. So we'll just plug -2 into here. So -3 times 4 minus 2 plus 3. So that's -12 minus, that's a great 12, minus 2 plus 3. So that's equal to -11. So now think back to yourself point slope form from algebra 1. Point slope form, you can use y minus y1 is equal to m times x minus x1 to solve for any equation at any specific thing given a slope. Well, the derivative tells us our slope, so we can figure out the m now just by plugging in -2, because that's our x. So -6 times -2 is 12, so our slope is 13. So that means that now, and you'll also see this notation. This notation means what's the slope at any one point. This means what's your derivative answer at a point. So in our case, f prime -2 is equal to 13. So there we go. So now we just plug it into point slope form. Y is equal to, or y plus 11 is equal to 13 x plus 2. Simplify things around. Y is equal to 13x plus 26 minus 11. Y is equal to 13x plus 15. That is the answer to the tangent line of this one. Okay, now I said I wasn't going to do any more, but I'm going to do one more just so I can show you how a certain thing would be done. Okay, here we go. The second and last problem, 2, is 14x, where happened to my voice, plus 18 rad x. And we want to find the derivative at 1, 32. Now, that just means we don't have to plug in 1 to find that there. We just know that it's equal to 32. Which it does equal 32. It's not going to trick you like that. It's literally just giving you the thing. So we need to find the derivative. So d of f over d of x, because we want to find the tangent line of this, of our function here, is equal to 14 x plus h plus 18 rad x plus h minus 14x plus 18 rad x. Okay, all over h. Now I'll simplify this down. 14x plus 14h plus we can't do anything really to that. 18x plus h minus 14x minus 18 rad x all over h. Now let's just simplify things further because those x's can cancel. 14h plus 18 rad x plus h minus 18 rad x all over h. Now, before we try to do something really fancy with this whole finding the thing and then just doing like 18 rad x plus h plus 18 rad x, that was a great radical sign, and then doing the same thing over to just try to multiply it, let's do a little bit of simplification so we can make this process easier for ourselves. So we can distribute the h to both sides. So by both sides, I mean splitting it down the middle right here. So we can go 14h divided by h. We can say 14h divided by h plus 18. I can put this in parentheses because both of these are 18. Rad x plus h minus rad x all over h. So we can simplify it like that. Now this simplified down 14x or 14h over h is just 14. And then now we can just find that one thing for this. So we'll go x plus h plus rad x instead of doing something really bad that we don't need to do. Okay, there we go. Now we've got a lot simpler things. And just know we can do this because remember at the end of the day this is equal to 1, which means we don't have to multiply to the 14 as well. Okay? I should have drawn smaller because I may have to erase all of this and then put it back up there and then restart a new line as if it were a freaking typewriter. So now let's just simplify this down. We'll go 14 plus 18, and then the entire point of doing it the plus is so that we can just multiply these two and those two. So we'll go x plus h minus x, because that's how those distribute, all over h times rad x plus h plus rad x. Okay, now these two x's cancel. You're left with 18 times h. So this here now is equal to 14 plus 18h over h, and then x plus h plus rad x. Okay, now these two h's cancel. You're left with an h over here and an h over here. What do you do with the remainder h? There's still an h there. So you would be tempted, because I just told you, to think that you did something wrong if you're left with an h here. But just know we've eliminated the h on the bottom. That's on its standstill own. But remember again, this h is infinitely close to 0, which means that at this stage in the game, because we've gone far enough to eliminate the h from the bottom over here, we can also eliminate this one. Because it's so close to 0, even though it still exists as a number, it's very close to 0. It's still close enough, sufficiently close enough to 0, so that we can just cancel it out. So now we're left with this over here. I'm going to do the erase thing that I said I was going to do. There we go. So then we'll go 14 plus 18 2 rad x is equal to this is our derivative. 14 plus 18 2 rad x is our derivative. That's as simplified as we can get it, although we can rationalize the denominator, but don't. Okay, there we go. That is our simplified derivative. It looks disgusting, but that's what it is. So we're going to box this. And now we're going to find what it is at 1, 32. So 14 plus, or the slope, is equal to 18 over 2, rad 1 is 2. So that means we're going to get m is equal to 14 plus 9, so that is 23 is our slope. And remember this is the slope answer here because that's what the derivative tells us, the change in the function, or the rate of change of a function. So slope is equal to 23, x is equal to 1, y is equal to 32, plug it into point slope, minus 32. is equal to 23 times x minus 1. Y is equal to 23x minus 23 plus 32. Y is equal to 23x plus 9. There we go. This is our finished equation. Now, that is how that works. Whew. Long video, because important topic. Even though the other video was longer, but we're not going to talk about it. So, there we go. That is derivatives.